What if you could instantly spot the missing puzzle piece in a sequence, no matter how jumbled it gets? Missing number is a classic Pattern Mastery 100 question and an interview favorite for Google and Facebook. Many candidates overcomplicate it, but with the right insight, you can solve it in a single pass, using simple math or bitwise tricks. Mastering this problem proves you see the bigger pattern, not just the details. Let's break it down. You're given an array containing n distinct numbers taken from the range 0 to n. There's exactly one number missing. Your task is to return that missing number. Now let's assess the challenge. A brute force approach might use a set or check each number, but that's extra space or n squared time. Can we do better? Yes, two clever ways. Math approach: the sum of numbers from 0 to n is n times n plus 1, divided by 2. Now subtract the sum of the array, and you get the missing number. Bitwise approach: XOR all numbers in the array, then XOR that with all numbers from 0 to n. Matching numbers cancel each other out. What's left is the missing number. Both ways are n time and one space, perfect for interviews. Let's structure the mathematical approach. Compute the expected sum from 0 to n. Compute the actual sum of the array. Subtract the actual sum from the expected sum to get the missing number. Or structure the XOR approach. Initialize missing to n. XOR all numbers in the array with all numbers from 0 to n. The result is the missing number. Let's try to implement it using solution 1. We begin by defining a class named solution. This acts as the container where we keep our method for finding the missing number in the array. Here we define a method called missingNumber. It takes an integer array called nums and returns a single integer, the number that's missing from the sequence. The array contains all numbers from 0 to n except 1, and our job is to figure out which one is missing. This line gets the size of the array and stores it in n. Since the array is supposed to contain all numbers from 0 through n, the length tells us the upper bound of the complete range. This line does two things. It computes the expected sum of all numbers from 0 to n using the classic formula. Sum equals nn plus 1 2 backslash text sum equals backslash frac n plus 1 2 sum equals 2n plus 1. This is like knowing how much money should be in a piggy bank if nothing is missing. It initializes a variable actual to 0. We will use this to add up all the numbers actually present in the array. This line loops through every number x in the array nums and adds it to actual. By the end of the loop, actual holds the sum of all numbers that are present in the array. The missing number is the difference between the expected full sum and this actual sum. This loop runs once for each element in the array, giving us a time complexity of n. Finally, we return the difference between the expected sum and the actual sum. If one number is missing, this subtraction reveals exactly which one it is, like noticing a missing puzzle piece by checking what's supposed to be in the box versus what's actually inside. And that's how this algorithm works. It first calculates the expected full sum of numbers from 0 to n, then computes the sum of the numbers actually present, and finally subtracts the two to reveal the missing value. Solution 1. Test case 1. Let's test our function using this input, 3, 0, 1. This array represents a list of numbers from the range 0 to n, except that one number is missing. Our task is to figure out which number isn't in the list. For an array of length 3, the full range should be 0, 1, 2, 3. The expected sum of these numbers is 6. The actual sum of the array, 3, 0, 1, is 3 plus 0 plus 1 equals 4. The missing number is the difference. 6 to 4 equals 2. So the number 2 is missing from the sequence. And that's exactly what our program outputs, 2. And the expected result also matches perfectly, 2, confirming that the implementation works exactly as intended. So, our implementation is correct. The algorithm successfully detects the missing value using a simple sum comparison, efficient and accurate. We begin by defining the solution class, which will contain our optimal XOR-based method for finding the missing number in an array. This method, missingNumber, receives an array that contains all numbers from 0 to n except 1, and our job is to figure out which one is missing. Here we initialize two things. N stores how many elements are in the array. XOR starts at 0 and will accumulate XOR results. The XOR approach works because XOR cancels out matching numbers. Think of it as pairing socks. Every matching pair disappears, and the unpaired sock, the missing number, is what's left. This loop XORs all numbers from 0 through n. Because we're iterating from 0 to n inclusive, This gives us the full expected set of numbers. XORing all these values accumulates them into XOR. Time complexity for this loop is O(n) since it processes n+1 elements. Now we XOR all the numbers present in the input array. Here's the clever part. Every number that appears both in the 0, n range and in the array cancels itself out through XOR. The only value that doesn't get cancelled is the missing number, because it never showed up in nums. At the end of both loops, XOR holds exactly one value, the missing number, so we return it. And that's how this algorithm works. It first builds a complete XOR of all numbers from 0 to n, then removes all numbers actually present in the array through XOR cancellation. Efficient, simple, and elegant. Solution 2. Test case 2. Let's test our function using this input, 0, 1. These numbers represent a nearly complete list of values from the range 0 through n, but with one number missing. Our task is to identify which number is absent. Here's why the solution works. This approach uses XOR to cancel out matching numbers. XOR has a special property. AE equals 0 and a 0 equals A. So the algorithm XORs all numbers from 0 to n, where n equals nums.length equals 2. We compute 0, 1, 2. Then it XORs all numbers actually present in the input, 0, 1. When we combine these, 0, 1, 2, XOR. 0, 1. The zeros cancel, the ones cancel, and we're left with 2, which is the missing number. And that's exactly what our program outputs, 2. And the expected value is also 2, perfectly matching the algorithm's result. So, our implementation is correct. The algorithm successfully isolates the missing value using XOR cancellation, efficient, accurate, and reliable. Alright, let's wrap it up. This problem was all about finding one missing number in a sequence, a clean logic puzzle that tests how well you think mathematically and bitwise. Breakdown recap. We started with an array of unique numbers taken from 0 to n, but with one number missing. Our job was to figure out which one. Simple conceptually, but it's a great test of how you handle efficiency and space optimization. Assess recap. We explored different methods. The brute force approach, while straightforward, isn't efficient. Instead, we looked at two elegant O(n) solutions, the mathematical approach using the formula for the sum of the first n numbers, and the XOR trick where matching pairs cancel each other out, leaving the missing value behind. Both methods are smart, fast, and memory efficient. Structure recap. The logic came down to this: calculate the expected total or XOR pattern, then compare it to what we have in the array. The difference, or the leftover bit, is our missing number. Implement recap. We implemented both approaches on LeetCode, and the code ran smoothly without any errors. Check recap. After testing across various cases, the results were consistent, confirming that both methods worked perfectly and efficiently. The key takeaway? When facing a problem like this, look for mathematical patterns or bitwise symmetry. The simplest ideas often lead to the most optimal solutions.